Welcome everyone to Cloud Computing and Big Data, our part 2 from lecture 1, talking about scalability driven by big data. But what we had basically in the first part today in lecture 1 was really talking more about cloud computing. So we looked a little bit into the computing aspects. We motivated that this is including cutting edge technologies like GPUs, for instance, and also, of course, still needed and required multi-core CPUs. And we also introduced these different technologies and terminologies. We talked a little bit about the different facets of computing, parallel computing versus centralized computing, and then maybe on a very bigger scale, distributed computing enables even more broader parallelism. So there are different terminologies that part 1 has already introduced, but we always had a certain view on the computing aspects, right? And made also some elements in terms of which layers we would like to compute something, an application on the SAAS level or different platform, Lego bricks, we say, on the platform level, and then maybe the bare metal or VM or virtual machines running somewhere on the infrastructure as a service level. So the first part is sort of very important to look to understand the second part also, but we shift a little bit the view now to the interesting term called big data. And big data was a term which many people actually called a long time a buzzword, right, in science and engineering. So many people said it's a hoax. It's anyway not, something which will be a problem in the future. But very quickly we came to the idea that the measurement device is getting much better. You see here one example out of my research group, the remote sensing elements, right? When you think about the satellites, their resolution on board of these satellites is getting much more amazing on a, let's say, yearly basis. So this says, of course, also the requirement for data is not anymore somewhere in the gigabytes. We're talking nowadays in terabytes and petabytes, right? And soon, probably exabytes, as I was alluding to our HPC system, when we have, let's say, the Jupiter exascale system. But the real definition was basically never clear and maybe will never be. It started with the 3 V's that actually characterize big data a bit more to the ground. So what is big data really, right? And the people have started, okay, obviously it's volume, right? The gigabytes. But what also was quickly going to challenges was the velocity. I will make a case for it. So how quickly is actually this data generated from measurement devices? And then the variety, right, is also a kind of form. We see more and more specialized sensors. We see more and more specialized data sets, which also were coming more and more to a challenge in computing. Then over time, of course, scientists have good ideas of writing paper based on another paper. They say, well, 3 V's are not enough. Let's add a 4th one. And when you have this 4, you need the 5th one. So they added different elements, validity. It should be proper data. Only then we call it big data and not noise. So you can also, of course, record something which would be, totally nonsense, and then we should not call it big data, although it would be still maybe in the petabytes, right? So veracity is, for instance, something where you also have to think about the different types of data and so on. So over the years, we came to, I think, maybe now 7 or so of these different versions. And with this, also the idea of, understanding it better. Here's also a very nice view on the more global view I get here from Wikipedia, for instance, where you have the idea of, doing this in terms of the different types of storages. But it all alludes to we have exabytes more and more, and this was already 2007, growing basically significantly. At the same time, you can imagine with big data, and now with all the different social networks and so on, we discussed in the prologue a little bit, the data is really growing in several applications. In some applications, it just remains, but it characterized a bit different than in previous times. You would have a sort of accumulation of data, right? You would have Facebook, for instance, it's accumulating data, right? While in some measurement devices, like a satellite, you measure this upstairs and you send it to a data center. You send it to another data center, and you actually do pre-processing, then you send it to another data center. So there are different, let's say, ways how to treat big data, and we will talk about this through over the course, that this makes, of course, fundamental differences. Once you want to accumulate petabytes somewhere, that's okay. But suddenly transporting petabytes to another center on a daily basis means you need very, very good internet connections, right? You don't want to do that on a daily basis. Hence, This has also something to do with big data and the data center design we will talk about. So that gives you a little bit of view what is now big data, although the real crispy definition is still something I think the experts argue about. Here are some examples, mostly also from research, but also, of course, elements that you maybe already know, and they all characterize the same elements. Some of you know, for instance, CERN, they have this collider, right, where they do and try to find the Higgs boson in high energy physics and now other things. They accumulate data in a data center, and it is basically then distributed to, let's say, in smaller pods to all over the world. So this is also requirements, data transport, not only accumulating. You see here one key challenge example of the square kilometer array that they want to build and actually started building, where we can expect 1 petabyte. That's okay, but we expect it to be there every 20 seconds, right? Now, when you see our tape archives with having 100 petabytes, this is okay, we can keep that. But if you multiply this very quickly, we will run out of capacity in all the tape archives, right? So this is something where you then have to think about, can we pre-process the data? There's maybe some noise in the measurement, where you then put computing in front even of the data storage to pre-process. And actually, this is also done in CERN. They not keep all the data that is basically done in these collisions. They basically, sample the data out. Now, on the other hand of the scale, and something alluding a little bit to the HPC course maybe, weather forecast gets ever more granular, right? So the grid we forecast on gets more fine-grained, more details, more physical variables. So this means also lots of more data. Or as you see here, we have also researchers in my group doing neuroscience, and the brains that we can do now in simulation, they go also to the petabyte regime, right? So this is also something where the simulation's getting better and better in the human brain research, but also requiring more and more and more storages. So you see all are very different in nature. And also you see the ISS here, of course, very prominent, standing for all maybe satellite and remote sensing elements. They need to, of course, now think always what they measure there needs to be coming down to Earth. So there's also more and more the idea that the satellites and the Earth observation elements have to have some pre-processing done before they actually transport all of that back to the data centers on Earth. So this is something which is one facet of the big data. Another one which is very important for you to know, because you will be much more driven by this in the future, is FAIR. Have you heard from FAIR in terms of data? Not really? Okay. So the fairness aspect is not like the sports fair thing. So this is more rather findable, accessible, interoperable, and reusable. So the idea behind is that many people, or many researchers especially, but also industry here and there, they kept their data silos, right, within the company, and nobody can touch it. You have seen, maybe some of you that have been there, Statistics Iceland, right? Yesterday had a presentation in the workshop. They're sitting on a huge data pot. And of course, other companies could leverage this data pot to do their own business on top of it. We talked about transport there, traffic jam prevention, but also if you think about all the cruise ships here that always come to Iceland, you can imagine if you have some statistics, you can immediately create interesting opportunities for SMEs. But this is something which needs to be pushed. Usually always want the people to keep their data and not put it fair. And this is an initiative from the EU and is actually forcing nowadays researchers massively in the EU projects. We have to give all our data open, right? That is a requirement. Once you sign and get the big check, you basically give all your data open. For health, of course, and medicine, there are still, let's say, some special elements in place that we don't expose patients' data, right? This is clear. But still, the whole research of measurement data needs to be exposed usually on these EU projects. And this is the same actually with journals, papers. The more you publish, you will see more and more they want not to have your results. They also want to have the real data or your AI models, right? So that you have to push and put out everything. And this is a FAIR initiative, which is, of course, by people like me seen quite interestingly. I have been blocked many times in the past in my research in 20 years because people don't want to share the data. Right? They want to publish on their own. And now by standing on others and working with others and having the data open, everybody can work on a much more faster pace. Hence, in your generations, I think you have a much more faster pace in this because many people are just forced to share the data. and cannot prevent it. There are also government elements in place to do this. Also, let's say this obligation in terms of companies in the future. So this would be quite an interesting area where we go in. But these is all elements where you would say it has something to do with big data, really on the data side. Now I would like to come a little bit again to the hardware side of the data, right? And I think it's important for you to understand this hierarchy. And of course, magnetic disks is a little bit old-fashioned. There are no other type of disks, but it doesn't matter. It's still standing for the large characterization of disks that you have, and tape archives that are basically taking the most data today, right? When you look in the big data centers, the storage, the most quantities of data are there. But as I said, when you want to do many small files or a backup on a tape archive, that takes you quite a lot of time. It has to be migrated on a tape. I don't know if you have seen it, but these tape robots take your tape, have to get it, right? Put it to a reader. Then you basically read or write on it, and it puts it back in the it's a very elaborate process. So this is very, very slow. And the same is actually true if you want to reuse things out of the tape. You cannot just, execute your job or do something. You have to wait until the robot get your data. And when you have, for instance, very many small files that can take up to hours to basically migrate it back to a real file system. So this is something to realize. And then, of course, the disks are the sort of thing we used to, right? We have almost all laptops have one. So this is something which is, of course, very convenient, but we see already a major capacity decrease, right? Compared to what we can do with tape archives, which is really in the petabytes mostly. And we talk about mostly terabytes in, disks, and this for quite a while. Now the main memory, and this is now the interesting thing, is we don't really associate with data so much. It's already very close to computing, right? But the capacity of memory is also very shrinked down compared to the disks. But this is needed, of course, to fuel the, let's say, the CPUs, and via device memory, also the GPUs, with data. So you always have to go basically through this. If you have systems which are then having cache, which is then really the fastest you can get in a way, from the data perspective, the registers are already very, very specific, very close to the CPU. You will see an enormous speed, but almost no capacity. Now you would argue, why is that, right? So why on earth we shrink the capacity here? And you will see NVIDIA with GPUs did enormous breakthroughs here of having more and more device memory. We call this HBM, high bandwidth memory, which are very close on a GPU chip, right? So let's say this is already lots of work done, but the trouble is that this is extremely cheap, also very cheap. You see a very increase, you can buy now as a normal person terabytes of disks, right, for a very cheap price. But if you go ahead of buying one for 100 terabyte, you still have to pay quite something, right? But for my memory, it's getting more and more expensive as well. And the more you go up for chip developers having cache on it, also the space is a problem, but also the capacity is a problem. However, the speed would be beautiful, right? If our systems would have tons of cache, but it's just too expensive to build. Hence, we have this cache, this kind of dilemma in computing, you would say, that with this storage hierarchy, we're still limited in computing. And this is now faced a lot with GPUs. You see that GPUs are actually perfect, right? And for some applications, it's just the best beautiful thing. They put many cores alongside because they don't get too hot. That means you can put more and more on it. But the trouble is they are starving. They don't get data quick enough, right? And this is a dilemma we are in now, especially if you now do parallel computing across many GPUs, right? Many of my researchers in remote sensing, they use then 128 GPUs in parallel. And we come to a point that we have computing enough, but we just cannot fuel them quickly enough with data. And this is a dilemma mostly coming out of this. There are storage hierarchies and so on. And of course, the second drawback that you remember a little bit, we have to always go via the host CPU to the GPU to fuel them with data, which is another stupid step, so to speak, that makes the GPU a little bit like we call it accelerator device. It accelerates certain things, but you always have to go to the CPU and do the main things still. And this is, of course, another bottleneck, but not reflected now, of course, in the storage device hierarchy. but they're all intertwined. And it's a very important element now in the course to understand these differences. Here's one example, what we also call then here, as I said earlier, the memory wall, with this different caches or the cache hierarchies, which fuel the systems, which are very, very fast, right? And of course, if you would, having bigger caches, there would be less cache misses. It would be perfect. But this has also alluding to another trouble in it, the permanent memory, the volatile memory. This is, of course, losing data now, right? Where we have different types of memory now, where we have even in research project network attached memory. So it's on the network, not anymore in the computer, because many people should use this memory. So there's lots of memory research done to try to fight against this memory gap in all. And this is something which, yeah, if you have good solutions, let me know, and you can get probably very rich these days. So this is still a very big problem for us all. So then just a little bit again to this elements. I think the most aspects I have already talked about. So this is, of course, the kind of different registers, and this is a CPU heart, right? Where then it's very close and filled by the registered over all these different cache hierarchies, as we call them, where still we see that, of course, it's getting much more cheaper in this direction, where this would be too slow for computing directly. You always have to use basically these elements to fill the CPU still today. And of course, it would be beautiful to have, as I was saying. So I think this is mostly it. Was already taught on the slide before a little bit. But this is understood. Are you with me so far? With cheaper, faster, and the different hierarchies? Oh, there's a question. Good question. So there's a question about the arithmetic units. So this is actually refers to the heart in the CPU. It is filled by the registered, and every arithmetic unit is then computing something. So, but there needs to be data to compute something, and there's a specific registers that are then addressed. And we're going here in the area of assembler, right? Where really, this is already machine-oriented code working on registers. But in this sense, there are these kind of, you would see it's also the clock speed coming in, where these arithmetic units are then processed. And with this, you would say that is where the data is really used, and then you write it back to registers and then read again. But yeah, and this is not the bottleneck today. That's why it's big and like a boat in a way in this graphic, because here we can now extend a lot, because CPUs get cheaper and cheaper, GPUs get cheaper and cheaper, but unfortunately the main memory is still very expensive. Also in cutting edge GPUs, if you want to have NVIDIA with lots of HBM, you are in a very high regime of paying the price for it. If you could make that better, then we could actually extend and do beautiful computing on a very much larger scale. Hence now the parallel computing idea, right? We are not bounded by one CPU chip. Let's have many chips. But then on the storage hierarchy, we still have the problem then that we cannot feed it still fast enough if we have big data. Even if you parallelize it and have, let's say, many, many GPUs in parallel, we're still bound by this faster, let's say faster, slower problem from the bigger storage devices. But good question. So, I mean, storage technologies, I think many of you have heard about. In the past, we had this magnetic disks. Now we have this kind of solid state disks. They are nice, still, let's say, quite expensive. Then this capacity growth that we have in the last 30, 40 years is really that we also put them closer and closer together. So the data centers today, you have really a full rack just of these disks, right? So they're very dense together, hence overheating again can happen every now and then. And that's why a data center, we talk about lecture 4, has then other problems, right? It has lots of capacity, but it has the trouble that in this area of disks, which is often used in cloud computing, every now and then they will fail, because you have this large capacity and it has to be disks, not just tapes, because you want to have data which is directly usable, right? But if they fail, of course, they have to be marked as not working and exchanged at some point in time. That means the rack needs to be opened, the and basically the maintenance should go. And that means maybe the whole rack is in maintenance, making less capacity. So in this sense, what you then find in cloud computing and data centers, and we talk about lecture 4 much more about this fault tolerance, resilience, elements where you basically have to prevent failure from happen, is an ingredient of every data center. And when we talk then about the computing paradigms like Hadoop and Apache Spark that are made for it, you will see that they exactly have this inherent, the fault tolerance. So if you submit a job and it will fail, it automatically resubmits the job somewhere else. Or the storage, you have replication schemes. So you don't have the data once in a block somewhere, you have the data twice or 3 times in different data centers and operate there with your map job or reduced job. But this is not clear to you. We see how that materializes throughout the course. It will come in lecture 5 when we talk about Hadoop. A very interesting material because this is exactly not what we do in HPC, right? MPI implications in HPC are absolutely not like this. One error in a CPU from a big application covering, let's say, the whole petabyte system, petascale system somewhere, means the job has to be stopped, completely renewed from scratch, right? Hence, this fault tolerance is just not existing in HPC in this application design. Of course, they also face every now and then overheated CPUs and have to put them to maintenance, but this means it will be not used by applications at all. That also is a key difference basically between HPC again and just cloud computing in a way. Let's come a little bit to other services every now and then, where we have here now storage and big data from the sort of academic and researchers perspective. It's a bit intertwined because also some companies can offer services in this European Open Science Cloud, like Telecom. You see, some of the industry is using it, but the European Open Science Cloud was primarily really done, as the name suggests, to open up research data, to enable scientists to have different services, to find data with metadata, to actually exchange data like Dropbox basis. So you load it up and another researcher can download it. Or you basically have elements like transfer. So you can really transfer, replicate between different centers, like the CSC in Finland. Here you see one proud host of our Lumi data center and so on. Open Telecom Cloud is an industry example. You see here B2Stage and B2Safe are 2 services operated under the European data infrastructure UDAT and developed there, but now also operated by CSC. There are different type of services that you need for this data. And we will talk about this much more when we come to lecture 10, right? So there are different aspects, but you know them from your daily life. You would use Google Docs, but not alone. You would use Google Docs with a Dropbox, or Google Docs with OneDrive, or Google Docs with something else. You would combine these different services. And of course, this is also to, let's say, support a little bit this FAIR directive that I mentioned, right? So this finding accessible, interoperable, and then also reproducible of results and so on by sharing this. Then when we have done now the academic version, I wanted to give you also an example, essentially, that is very commonly known in Amazon S3. People know from S3, have heard from S3, not from me only, but from other things. Yeah, sort of a data storage interface from Amazon that stand the test of time now. You have this in different types of interfaces, mostly REST these days, but in traditional times there were also SOAP, and it's essentially a bucket store. So you could put something like a bucket into it, and it scales up, scales down. You don't think about the terabytes or so that you would have on your hard disk. You can put up MP3s there, images there, and like a bucket, it will be just stored. Now, the benefit that the cloud, of course, gives you is then these ingredients, right? This S3 service is highly scalable, which means scaling down, scaling up in both directions. It's also durable, so because they have different centers, as I was showing you in the video, they of course can have lots of replications of the data. And given they have lots of security standards in place, it's also a very secure solution, right? And easy migration is in a way that S3 became more or less a sort of de facto interface for this kind of storage devices and so on. You will see many others that leverage, let's say, tools. They actually hook on the S3 REST interface. And we will talk more about it, obviously, in lecture 8, when we have then this infrastructure as a service and how it is bound to this storages via virtualization layer, so that this could be also multi-user, right? Again, you want to share it, maybe your MP3 with your girlfriend or so collection, whatever it is. This is something where it's a quite nice service and a very popular service in the storage domain. And this is something where we will come to later also in lecture 8. It has, of course, some other features, and there are other elements as well to talk about in terms of storage now, not computing. Then we had the prologue lecture already with an interesting question. I think the question came up by one in the audience: what happens if I want to build my own cloud, right? There was one student in the audience. He is not here today, but they're building their own cloud. So what could be, let's say, elements which you can reuse for this, right? And this is OpenStack. So OpenStack gives you lots of different services we will talk about. I put some here and highlight those here now here on the storage front, where you have, again, the same ideas like object storage. And we talk about these different storage types also in the different lectures. Swift, Cinder, Manila, these are all different, let's say, implemented software pieces that you now can combine together very easily to create your own cloud at home or at your company, right? And this is a very nice thing, because you don't have to implement, again, this kind of scalability aspect, shrinking with need, and you know, upscaling with need. It also supports the different elements in terms of hardware on the computing side. You can actually work with bare metal, virtual machine, or containers, right? For each of them, we will also talk a little bit in all the subsequent lectures. In lecture 8, bare metal. Later on, you remember, we have Docker containers, Aptena containers, and so on also in the course. These are different levels how cloud providers today deliver their applications with kubelets and so on. But this will be, of course, later material. We have to start with the basics. But that's why I also want to convene it at the beginning, that you will see many of the elements that you see here, let's say working with a compute, then virtual machines from Nova or the Sun service and so on. They all are based then, of course, again on CPUs or partly now of GPUs. So it always comes back to the basics. Of course, there must be really a computing device. A cloud is physical. You don't experience this because you just have a website somewhere, but somewhere is real hardware. And managing all of this can be hell a lot of software to implement. And for this, OpenStack has actually quite many services already available. It's much more than those that you see here. Also, the whole, let's say, monitoring aspect of it. What happens if the cloud fails? What happens with authorization, security, authentication of users? All of that is already implemented, and you just basically, again, like Lego, you pull it to your needs of your company, and then you're done. But we will talk in lecture 14, of course, much more about it. I think there's a question from the audience. It says, what type of application would you build your own cloud for? And what type would you use it with other clouds out there? Is there any definite answer to this? That's a good question. There's even several terms for it, which we will see how they materialize over the course. We call them public cloud, private cloud, and hybrid cloud. I don't know, have you heard about this? Public clouds, yeah, some of you. So we call Amazon, MS Azure, all these big cloud providers in a way public clouds, right? So you would say they deliver almost all services already. Why on earth should I deliver something on my own, right? Why I should implement something on my own? And this is a good question, because you will see there's many data, sensitive data available. For instance, you say you have a health SME, which has lots of patient data, patient databases, or other elements are finance that don't want to share anything, or other elements are actually Porsche, for instance, they don't want to reveal their next car design, where they, for certain aspects in computing, would definitely use the public clouds, but they would never upload their data there, not the complete data set. Hence, they would be having something called private cloud inside the company. Usually this is, and we talk in one lecture about it actually, about this classification in these 3 categories. The private cloud is mostly something where the company was something inside, which is, for instance, around sensitive data you don't really want to share or are not allowed to share, right? I mean, some may have data from 66 North and don't want to upload that, somewhere into the Amazon cloud, everything, because they probably don't like that very much. And this is one of the reasons. Another reason is cost. right? You will see for some reasons scaling up and down. For instance, some of you know, some companies have this tax thing coming up. They have to report everything, then suddenly need lots of computing. And then you have a peak sometimes in computing, right? Where you say, well, normally we can maybe do our own cloud. It's much more, kind of cost effective to have our smaller services. But sometimes, unfortunately, I have to bridge out, right? I have to serve the peak users. I have to serve the peak tax reimbursement stuff. And then you need lots of compute, but only for a month. And for this reason, there's also this sort of idea connecting your internal cloud with the public cloud. And that's what we call then in the end a hybrid cloud that you use, because you use for some services just internals. Let's say some call it partly even intranet today, and the services they are running is basically nothing else like a private cloud. But in some occasions, they will bridge out with the S3 interface or storage, or for computing need like SC2, as we have seen in Amazon, to get this, let's say, they are computed. These are two reasons. I think there are a couple of more, but I hope the idea is a little bit clear, so that you don't want to share, let's say, everything within the cloud. I hope that was okay. This is answer your question, Azur? Okay, good. Right, so, and we will talk more about these differences. And of course, today I would say many applications use even different offers. Just another idea of big data, because this the second part is around big data. We have talked about measurement devices and elements. Now we're talking more about people, right? And here's the idea of the social networking about media, people, sharing. This is totally out of control in a sense that you see in traditional database modeling, SQL, structured query language. So people want to have a field for everything, address, phone number, what is it you store? And you would have, basically these kind of different homogeneous data storages. And they still remain for many purposes. Let's say retail data. These definitively have their saying and still SQL. But for some of the social media elements, this is not really practical anymore. So you will see here in Facebook, there's just one example, but all of these. Twitter, by the way, as you know, is X nowadays. Which has had also caused some interesting trouble in the community about data, right? Who owns the data? What we have shared over all the years is now in the hand of Elon Musk. So that's interesting. But nevertheless, these are big providers of big data. And the structure inherent is more like a graph sort of thing, right? This with the likes here is just an example of who likes who and who has actually tagged who in a picture and so on. The details, I think I don't need to go into anymore. Everybody of you is almost on Facebook, but the structure of the data is growing unsystematically, and you have to be prepared for this in the cloud, right? And this is something also we talk in lecture 15, how Facebook actually could scale up with this. So you have to imagine you have millions of users, and when you click this, the other one directly sees it, right? So this is something which requires a massive data engineering design, and they have a big team there that is actually working alone on all of these designs, and we'll talk in lecture 15 about it. But it's a complete other and more recent new type of big data that we face, right? Which we actually in one respect not really can fully control yet. Also, if you think about, there would be regulations more and more coming in. Some of you have heard about GDPR, maybe, General Data Protection Regulation, right? Where you have to give informed consent that your data is used. But have you given your data maybe 10 years ago in Facebook, and then you have to find it again? Maybe it's some specific post. This means lots of crawling to find that, right? So it's something which is also not completely clear how actually Facebook and the others usually should deal with this. Hence, they usually opted out and say, by doing so, you contribute your data forever, so to speak, right? And this will be in the future also much more regulated, because there's, of course, some danger. One of the examples is the right to be forgotten, right? You can actually talk to them and say, I want to be completely removed by tomorrow. And this is a data center challenge, to remove a person from the social network, right? Your like suddenly is in the nowhere. And so on. For computer scientists, even it's a lot of interesting, tricky things. But we will talk about this in lecture 15, just that you understand the nature of big data is really completely different in all the other different facets. And with this also the need, of course, for scalability. we talked about, again, data locality versus, transfer of data, accumulating data in one position. That's easy. Data locality we should therefore use, and maybe put the computing to the data, right? And that is something which we will explore then with Hadoop, with this MapReduce paradigm, where you just think much more about something we call big data analytics, right? So where you then basically think about, okay, let the data be there, perform smaller operations closer to the data, and then take the aggregated solution, hence divide and conquer, HTC comes again in, and take then this result and combine it to something before you transport, let's say, petabytes to the HPC machine, do perfect algorithms and transport petabytes back, right? Which would take in a typical internet many, many hours actually to do that. Hence, this is an important principle we'll talk a lot in lecture 5, then again lecture 6, and also about the two terms where you basically see a little bit here difference. Data analysis that you may know, really looking on the data, doing some, regression techniques or so, is often also bound to sort of causality. And big data analytics, because it's extremely distributed, sometimes has a fashion of being a little bit more correlation oriented. So it has no causality really. And I would like to give you an example because sometimes it's a bit hard to understand from my understanding from students. So here you have a perfect example of a big data analytics example. So you would say the parable of the Google flu was several times published, where people had a problem in detecting the flu at that time from the, let's say, authorities, right? It took many different doctors through many different, hierarchies to say, here's the flu in that numbers. Now, then Google came along and said, well, that's very easy for us. We looked in our perfect databases, and these are the regions with the most flu. Why they did this and how they could do this, that of course, most of the people want to search for it, right? When you have the flu, they have a search query and say, well, what is this flu and so on. And by actually identifying all over the world what people are searching, they think, okay, these people have the flu. Even if this is in the gray, sometimes people, maybe it's your sister next door, you would still Google it, is one more, one less. In this world record, not a problem. But, and now comes a parable on this, why it's big data analytics rather, and the correlation and this idea that there's some flaw in it maybe. Of course, here it was shown that many people just phoned, right? Or basically messaged someone else on a complete different area and said, hey, by the way, I have the flu. And then the other people remotely search for the flu, right? And it could be shown that actually this kind of looking at the data, because data speaks for itself, it's a sort of meaning, is actually a lot of noise and not really usable to predict the flu. However, of course, the speed was tremendous, right? They could give direct indicators to the governments and say the flu is now there, widespread. But the data was heavily biased. And biased is a term we also come back to when we talk about machine learning. We say rubbish in, rubbish out in these elements when we search for causality for really modeling. But we will go there step by step. And this was just an example of these elements. And this was also then the birth of Hadoop, of Spark. We will talk in the course in lecture 3 already very soon, which is then about distributed processing and most likely with MapReduce these days. But people also have started to use Apache Spark a lot. But again, as I said, it needs in-memory processing. You see it's much more faster compared to Hadoop. And the details we will go into the different lectures, but Spark really lives from memory. Hence, you have to have a CPU with lots of memory. And as we discussed before, what's the problem with having a CPU with much memory? Yeah, and you go and pay the price for it. And we will see it in the lecture. I will give you the examples in the cloud, how much it costs if you add more and more memory. That's where the check comes. Already in the, in the prologue, we already talked about the divide and conquer idea behind it, the key ideas behind it, which makes then the interesting idea of having this map, sort, shuffle according to keys, and then reduce approach. And these maps and reduces can run everywhere. That is small chunks of computing that are meant should be operated close to the data. And by the aggregation in HTC terms, with this conquer result, then you come to the result of the overall problem with the partitioning. And we will talk about this, of course, much longer in this respective lecture 5. But we start already earlier with lecture 3, a little bit to give you the assignment also earlier, which would be on HD Insight, just at the end here of the the lecture just to give you a little bit the idea what's coming up. So we'll talk about MS Azure HD Insight, which has a Spark implementation. Before this, we look a little bit into the basics of machine learning to use that really. And then we will use some of these kind of services in the cloud and also the file systems, where Hadoop is a very important factor, because it also gives us not only the MapReduce engine, but also the Hadoop distributed file system we will talk about. So a storage solution, which then implements essentially the idea of this data locality. So then we will have in the next lecture, just as a sneak preview, then the idea of having now classification, clustering, regression better understood. This is also something I already talked to in the prologue. That's of course the tools in machine learning you use basically to understand data, to work with data, to learn from data. And all of them have also an intertwine in different computing needs, as we will see. Right, so this is also similar like we have seen in the prologue, and I was alluding this already. There are different facets of learning. Just one more sneak preview of something important for machine learning, then we are close to the end. Supervised learning, unsupervised learning are different terms, which we will reveal also when we talk about machine learning. But there's this kind of theme where I talk to you that this neural architectures, neural network architectures can be very different, right, for different problems. Hence, we will talk also about hyperparameter optimization then in this context at the very end of the course. But this really consumes then lots of computing power basically on this big data. That's also interesting and intertwined with this. Again, if you want to look ahead a little bit, what's coming in the next couple of lectures, again, we will use Apache Spark with HD Insight, and it always follows the same scheme. You basically have a sort of subscription, a pay per use of resources. Of course, for you, it's free in the course. Don't worry about this. Then we deploy a Spark cluster together with HD Insight, which I pre-configure for you and give you access to. Then we have this PySpark kernel in a Jupyter environment. So you have basically Jupyter notebook, and inherently you use then actually Python and Spark. You create a session, then you have the application data sets loaded into and perform some machine learning model on it. It will then run in the cloud, and then essentially at the end, you have some evaluation, refinement, maybe resubmitted, and so on. And this is a sort of stepwise approach. We will come back again and again in lecture 2 and lecture 3, so that you have a sort of modus operandi how that works. And the motivation is, of course, clear. We want to do this with bigger data sets, not those that usually fit on the laptop. I have a short video if you have time still, but if you have to go to the next class, I understand this as well. But yeah, we have our next class together, right? Yeah, true. Yeah. So I will play just a short video, and I think in the third lecture, we anyway will not, we'll use the third hours very much. You see here still maybe a short pointer, all this lecture bibliography parts I mentioned, right? So instead of buying a book, consider looking at this. And I maybe should also acknowledge all my students. They helped me tremendously over the years here for the research group, really to also have some of the materials you see in the course.